Mrinal, please start.
Thank you, sir. Good afternoon, everyone. Welcome to the weekly online lecture series, which is jointly organized by Savitribai Phule, Pune University, and South Asian Meteorological Association, SAMA. Today is the 19th lecture of the lecture series, which will be delivered by Dr. Somenath Dutta, sir. This is his fifth continuous lecture in our lecture series. Today's lecture will be focused on baroclinic instability. Before we proceed with the lecture, I would like to request President of SAMA, Professor Ajit Tyagi sir, to please deliver the welcome address.
Thank you and welcome to Somenath and all. Uh, I think our organizing committee members and of course very important all participants and students who are attending this series of lectures. One thing which I'd like to point out that this atmospheric dynamics program is coinciding with the very dynamic atmospheric conditions of the monsoon, and therefore request all of you to go through the synoptic situation or the weather situation which is happening and trying to relate what you have learned or what you are learning, because this is one-to-one correspondence. Whatever is the dynamics, it is getting manifested in the weather phenomena through the synoptic features. Like recently we had a low pressure which intensified into depression, moved northeastwards, or northeast India gave heavy rainfall, and this is what is very interesting phase. It's not only the theoretical teaching which is going on, but we have to relate with the actual weather. And this is what you can do. You can go to the IMD website, see and try to interpret whatever you learned and relate with the given situation. So once again, make full use of this series of lecture. And today is on very important topic of baroclinic instability, which is, I think, major factor along with the barotropic stability, which is in the tropics, but baroclinic is worldwide instability, which dominates the weather systems. So over to you, Somnath, and
Yes,
once again, thank you for delivering the lecture.
I hope this whiteboard is visible to everyone.
Yes, sir. Yes, sir.
So, baroclinic. So, before baroclinic instability, I should tell that what is a baroclinic atmosphere. An atmosphere is said to be baroclinic if there is horizontal temperature gradient. If there is horizontal temperature gradient. Temperature gradient. That means, in a very simple language, that means at any level, temperature between 2 points are not same. As such, this is a realistic condition. And if it is not there, then we say it is a barotropic condition. So as such, we all can understand that purely barotropic condition doesn't exist at all in reality in our atmosphere. Only baroclinic condition is also, because in the atmosphere we just cannot imagine that all points over the globe will have the same temperature at a given level. So it is not. So now question is that 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 is a that whether this horizontal temperature gradient is more or horizontal temperature gradient is less, this matters. That means a measure of baroclinicity, it is actually matters. Measure of baroclinicity. And measure of baroclinicity in a very, very practical way. uh, it can be measured. Very simple thing. So suppose I am an operational forecaster. As an operational forecaster, every day I am supposed to analyze the temperature field. I am supposed to analyze the pressure field if I consider the mean sea level chart. And if I go for upper air, say upper air, then I am supposed to analyze the geopotential field, that is jet field, geopotential height, and also temperature field. So now suppose I have drawn the isolines of geopotential height, isolines of temperature. Now I can demarcate my region, some region. Instead of globe, I can demarcate some region like this. Suppose I have demarcated this. This is my region. This is my region, and in this region, these are my iso contour analysis. That is height, yeah, height analysis actually, height analysis. These are my contour analysis. Say, and suppose these are my isothermal analysis. These are my isothermal analysis. Isothermal analysis. So now, if the situation is like this over my region, then I am very much welcome to say that over my region, there is no temperature gradient. Across temperature gradient on an isobaric surface. Because here we can see the pressure lines, that is isolines, and this temperature lines, they are parallel to each other. So then this is a purely barotropic condition, which you will never get. Now let us consider another one situation. Another one situation. Another one situation is like this. This is my contour analysis. And say these are my isothermal analysis. Say these are my isothermal analysis. Analysis like that. So first of all, one thing is very, very clear. That since the isothermal lines are cutting the contour lines, so therefore it is a clear-cut baroclinic atmosphere. This is number one. But now let us consider another one case. Another one case. Another one case, let us take. So now I could not draw it properly. In both cases, we can see that isolines of the temperature and the uh, isolines of the contour line, that is height lines, they are cutting. But I should just a minute. This is not a good example. I should explain much better way. Just a minute. Right there actually. So, but what we see that angle of intersections are not same. Angle of intersection in this case, it is more than the angle of intersection in this. I could not draw properly, please excuse me. This angle of intersection between the isolines of the temperature and the isoline of the height field, this is a measure of the baroclinicity in the atmosphere. More the angle, that means more the baroclinicity. More the baroclinicity. Now, we all know in case of monsoon, what happened? We know that it is being said also that monsoon is a gigantic sea bridge. It is a very kahavat is there. Monsoon is a gigantic sea bridge. And we all know that the mechanism of the or dynamics of the sea bridge. So here also the same thing happened. During summer season, our ACL landmass and the Indian landmass especially and the North Indian Ocean becomes warmer, very much warmer than the southern hemisphere ocean. Because southern hemisphere there is that time your winter season is there. We all know. So as a result of which, what happened? There is a strong thermal gradient is there. North-south temperature gradient is there. Very strong north-south temperature gradient is there. Now, this north-south temperature gradient, where this north-south temperature gradient, it implies that our monsoon environment is a baroclinic environment. That means mean flow in the monsoon season is baroclinic. So for analyzing the baroclinic instability, first of all, what we need a baroclinic mean flow, not unstable. Again, I am telling you, baroclinic mean flow means a mean flow across which there is temperature gradient exists. So this is your first need, a baroclinic mean flow. So now, baroclinic mean flow we require. So now, if the mean flow is baroclinic, then we all know very well. That means when there is a temperature gradient, already that topic has been covered. I understand. That is thermal wind. So therefore, there will be thermal wind. So now let us consider westerly mean flow. Now consider westerly wind flow. Westerly wind flow means zonal flow is only westerly. Westerly wind flow is there. And northern side, as I told you, suppose northern side is, in generally northern is colder than the southern side. So northern is say cold. Southern is your warm. So now suppose, so due to that, already due to this north-south temperature gradient, there will be thermal wind. And we all know very well, thermal wind will be in such a way so that to its left, there will be cold. That means thermal wind will has to be also like this one. So this is your thermal wind. These are all your thermal wind. Thermal wind is there. So now what happened? Now suppose if you increase the coldness of here, that is if temperature you are put down and here if you temperature increase, then what will happen? This north-south temperature gradient, it will increase. So as a result of which, that is your strength of the thermal wind will increase. Strength of the thermal wind will increase. Now, when this north-south temperature gradient, exceeds certain thresholds, certain threshold, threshold. This threshold again depends on the mean zonal wind at what is the mean zonal wind and what is the latitude. These two things, it depends on these two things. Okay, so when this horizontal temperature gradient exceeds certain threshold, that means the thermal wind, this also exceeds that threshold. Let us say this is your UC, which depends on, as I told you, these two quantities. Okay, then what happened? This mean flow becomes unstable. This mean flow becomes unstable. So when this mean flow become unstable, then it behaves just like wave type. So how? I will show you now. So then instead of zonally oriented, you will get wave-like structure. Wave-like structure, and which are known as mid-latitude baroclinic wave. So this type of wave, you will get, and these are your baroclinic instability, baroclinic unstable wave. Now, now see, once these wave are generated, wave forms, then before that, actually, one thing I would like to tell you, there is a concept. The concept, name of the concept is I will tell you in my next lecture, available potential energy. Let us forget about its exact expression, but let us remember one thing. This expression looks like this. Some constant is there. There is some constant is there. And then there is an integration is there. This integration is from surface up to top of the atmosphere, that is P top. And here, this is important, let us understand, T prime square bar, this is nothing but stand variance divided by 2 into sigma into P, mean pressure field. Mean pressure field, we all know, sigma is the static stability parameter, which I have already discussed. And this T prime square is the most important thing. This is the variance. We all know how variance we are calculating. And this is the vertically integrated variance. Variance, how you will calculate? Very simple thing. Let us take first one level. Let us take 1000 HPA level. Now at the 1000 HPA level, let us find out what is the temperature at each and every grid point. So let me say this is equal to IJ 1000. This is the temperature at the ijth point at 1000 HPA level. Now what we do, first we take their mean. I don't know how many people take their mean. Mean means here it will be areal average. We will take its areal average divided by some m into n something is there. Areal average will take. So let us take this is equal to T 1000 average. This is the areally average temperature at 1000 HPA level. And then what we do, from every such IJ 1000, I just subtract this one. This we also subtract this mean. Then we will get the departure of temperature at the ijth point at 1000 HPA level from its areally averaged value. a really average value. Now, some of them may be positive, some of them may be negative. Hardly it matters. Then you just square it. Just you square it. So now it becomes a perfectly positive quantity. And this you will get for each and every ij. Then you take their average again. Aerial average you do. Yeah. So you do 1000 square. So again you take their aerial average. So what you get it, this you are getting the variance of temperature at 1000 HPL level. So now one thing is very, very clear. Had our atmosphere been a purely barotropic atmosphere, then in that case, this would have become 0. Now this thing you have to do for every level. For every level if you do. And then you integrate, you just add it for every level. Add it every level. Okay, and this is approximately at least qualitatively it is representing this quantity. So therefore one thing is very, very clear, that more the temperature gradient, more will be the available potential energy. Okay. Achha. So now if we remember our last slide here, we have actually increased that horizontal temperature gradient. As a horizontal means I have increased here north-south temperature gradient. Okay. Now this north-south temperature, existence of north-south temperature gradient ensures some available potential energy, because this north-south temperature gradient definitely gives rise to some temperature variance, and this temperature variance gives rise to some available potential energy, and that available potential energy we call it zonal available potential energy. Zonal available potential energy. And this zonal available potential energy, let me denote by A with suffix Z. A with suffix Z. So now when I am going on increasing the north-south temperature gradient, actually what I am trying to do, I am just trying to increase this AZ, okay? And once AZ also exceeds certain threshold value, then we are getting this wave-like structure. So now see, that is one very interesting. Now, once the mean flow becomes unstable, then what is happening? Once the another means, then what happened? You know, look at here. Here, actually, this is the wind direction. Am I correct? This is the wind direction. So now, if you split it into two components, then you will find there is one component from north to south. North to south. Not only that, here there is a component from south to north. So that means what happened? Due to this instability, winds from north are coming to south, and winds from south are also going to north. What does it mean? Winds at the northern latitude, they are colder, but winds at the southern latitude, they are warmer. So as a result of which, that means what happened? When relatively colder air from the northern latitude are coming to relatively warmer southern latitude, and relatively warmer air from southern latitude, they are going to relatively northern latitude. As a result of which, what will happen? What will happen to our north-south temperature gradient? It is very, very clear. This north-south temperature gradient will reduce. And this reduction in the north-south temperature gradient will results in what? Results in a fall in the agent. Fall in the agent. Now question is, if there is a fall in the agent, then where it has gone? After all, it is energy. One thing I have to tell that this type of orientation you will not only find in the geopotential height or wind field, you will find it in all the scalar field, wind temperature, humidity, etc. So if I draw the temperature graph also, it will be like this. This is one isotherm. This is another one isotherms. So like this, suppose this is your T naught. This you may say T naught plus delta T, like this, delta T, like this. There are many. So now let us try to see one thing, that now this is then in that case, this will be the colder part of the wave. This will be the warmer part of the wave, sorry. This will be the warmer part of the wave. This is similarly, this is your cold. This is your warm, cold, warm. This is cold. This is warm. So now let us understand one thing. Before this situation, you remember that our isothermal fields are also oriented like this. We all know very well. We know very well our isothermal fields are global isotherms are more or less oriented parallel to the latitude circle. This we know like this. So as a result of which earlier we had a very clear cut cold one. Cold was to the north, warm was to the south. That means temperature gradient was directed in the north-south direction. There was no significant temperature gradient in the east-west direction. It was in the north-south direction. But when we have the wave field, this field, then we can see there are temperature gradient in the east-west direction, isn't it? East-west direction. Again, this east-west direction temperature gradient, this will also results in some another type of available potential energy. Of course, this another type of available potential energy, this we call AD, available potential energy. I repeat, AD, available potential energy. And this AD, available potential energy, let me say this is equal to AE. So now we can see AE is not equal to 0. But in earlier case, AE was 0, almost 0. It is almost 0. So therefore, what happened? There is some increase in AE. There is some increase in AE. So now we got our answer that whatever fall was there, where it has gone, that means it has gone from AZ, it has gone to AE. It has gone to AE. Okay, so we got it. So now another one thing is also happening. Now we also know that ahead of the trough there is divergence. That means here divergence takes place. Similarly, here divergence takes place. There will be divergence. There will be divergence. There will be divergence. And we know very well that divergence means expansion, outflow. If air outflows, then there will be expansion. And we know very well that expansion leads to cooling. Expansion leads to cooling. So there, and of course I have not written there is convergence. Convergence. There is convergence. This convergence. Convergence. So there convert, and due to convergence, convergence leads to compression, and due to compression, heating is taking place. So therefore, one thing is, again we can see one thing, that over this region there will be cooling. Fine. Over this region there will be heating. Over this region again there will be cooling. Over this region there will be cooling. So now interestingly we can see cooling is taking place over the warmer part of the thermal wave. Cooling is taking place over the warmer part of the thermal trough. So therefore, if it is happening, then what will happen? Then again, this east-west temperature gradient, it will be reduced. So if the east-west temperature gradient is reduced, then what will happen? Then again, what will happen? This AE will come down. AE will be reduced due to this process. So now again question is, if AE is reduced, then where it has gone? Where it has gone? Now look at here. Now suppose over this region, if divergence takes place, okay, this is an upper air flow I have. So therefore there will be rising motion here. And over this region, if convergence is taking place, then there will be, what will happen? This will be motion. So as a result of which, one typical vertical circulation will be set up. One typical vertical circulation will set up. Typical vertical circulation will set up. You can see vertical circulation will set up. So now question is, now vertical circulation, though it has set up. So if vertical circulation has set up, then what happened? That means for maintenance of this vertical circulation, for generation and maintenance of this vertical circulation, you require kinetic energy, isn't it? You require kinetic energy. Without that, it cannot be generated and it cannot be maintained. Okay, kinetic energy is required. And since this kinetic energy is across the wave field, this kinetic energy is known as eddy kinetic energy. Eddy kinetic energy. And let us denote it by Ke. So therefore, these two things results in these two, that is reduction is A and increase in Ke. So therefore we got the reply. What reply? This AE goes to Ke. So now question is, if it continues like this, then after some time definitely this will be off. And this instability will go. So now if I want that instability to continue, then somehow AE needs to be maintained. That means whatever loss of AE is taking place due to this conversion, that loss needs to be compensated. So for that, what you require? You require that in the wave part, temperature wave part, wherever cold is there, there should be supply of cold air, and in the warmer part of the temperature wave, there should be supply of warmer air, relatively warmer air. And we know very well the source region for the warmer area is over equator southern latitude, and source region for the colder air is to the north, in the northern latitude. So therefore compensation is possible if there is cold northerly advection and warm southerly advection. In mathematical term, we say like this: V prime into T prime bar, that this covariance, it should be positive. That means northerly cold, southerly warm. If it happens, so what does it mean? This is possible if the temperature trough, temperature thermal trough lags behind the contour trough by certain phase. So this is a very important criteria. So that's why we can see also that upper level westerly trough tilts towards west. Why it is so? Because we know trough always tilts towards the warmer side. So, and since the warmer side is to the sorry, I am extremely sorry, please excuse me, trough tilts towards the colder side. So therefore, and since the colder side is to the west of the trough, westerly trough, so that's why westerly trough tilts westward with height. Okay, so now with this background, actually now our question is baroclinic instability today. So now baroclinic, so from this picture itself, now we can get the definition of the baroclinic instability. Baroclinic instability is defined in this way, that is, a mean zonal flow field is said to be baroclinically unstable if a small perturbation introduced in it grows spontaneously by extracting the available potential energy from the mean flow. We have seen also it has grown at the cost of the zonal available potential energy. This is the definition. So now question is how we analyze. I am not going to analyze it because its analysis is a little bit mathematically critical. This I am skipping it. I have already provided some material in the material details, but I will tell you definitely for analyzing this baroclinic instability. What happened? We consider our atmosphere. Atmosphere consists of two layers only. Atmosphere consists of, suppose this is your ground, this is your mean sea level. Okay, mean sea level, pressures, let us say 1000 HPA level. So one layer is from mean sea level to up to 500 HPA level, and another one layer is from 500 HPA level to 0 HPA level. So these are the two layer atmosphere. So now this layer is represented by an imaginary level located say at 750 HPA, and this one is represented by another one imaginary level represented by 250 HPA level. Okay, and generally these levels are indexed. These levels are indexed. Suppose this is indexed as 0, this is indexed as 1, this is at 2, this is at 3, and this is at 4. These are the index. And what we do, first of all, we put a boundary condition here and here. Here we put boundary condition that vertical velocity, that is omega, is equal to 0 here, and here also omega is equal to 0. Okay, and what we do, that is at this level we specify geopotential height phi. At this level we specify at every point geopotential height, and this geopotential height we shall denote it by phi 3, and at this level also we specify the geopotential height, that is phi 1 we denote. And what we do, this we just divide it by f0. F0 is nothing but that is your Coriolis parameter for the reference latitude. Okay, and let me denote it by call it psi 1. Similarly here also f0, this we call it psi 3 at this level, and at this level we specify omega. So therefore, how we are, that means try to see, we are not specifying all the fields at every level. At the lower level, we are specifying only omega. Second level, at that we specify in the geopotential height, then omega. That is so actually this is called, this type of gridding has a name. This is a staggered grid. NWP experts, they know better than me. These are called staggered grid. Okay. So now what happened? That actually for analyzing the baroclinic instability, you remember, for analyzing the barotropic instability, we made use, yes, Wing Commander T.R. Rahman raised hand. Shall I, sir, answer your question after my talk, or right now you want?
So we will take questions in the question answer sections after the lecture.
Okay. It is okay?
Yes, sir.
Okay. Thank you very much. And what happened, that is, as I was telling, that for analyzing the barotropic instability, you remember, we made use of one governing equation. That governing equation was nothing but your non-divergent barotropic vorticity equation. So here also we have to use some governing equation. Since it is a two layer, so here we use two governing equation. I am not going to write these two equation. I have shared the notes there, you will find, but just I am naming only. At the level number 1, we are applying quasi-geostrophic vorticity equation. Quasi-geostrophic vorticity equation, where only this phi field is required and omega field is required. And similarly at the level number 3 also, we use quasi-geostrophic vorticity equation. And here we are using another one equation, that is, name of the equation is thermodynamic energy equation. Thermodynamics energy equation we are applying. And then we did lot of mathematical analysis are there. Very interesting mathematical analysis actually. And after the mathematical analysis, as I am, since it is an instability study, so therefore we have to use here perturbation technique. Perturbation technique we apply. So perturbation technique, when we are applying perturbation technique for the level 1, that is your level 1, our wind field we are making like this. There is one mean wind, and then there is one perturbation, then V1 prime, and then 0. Here also same thing, U3 prime, U3 bar plus U3 prime, then your V2 prime and 0. So what does it mean? It means that at the level 1, that is 250 HPA, we are having only mean wind, zonal component, no meridional component, no vertical component on the mean. But in the perturbation, we are having a zonal component, U1 prime, meridional component, V1 prime, no vertical component. Similarly here. And here we specify, we require to specify only omega. Here omega means only omega 2 prime. That's all. That is perturbation vertical velocity, because in the mean there is no vertical velocity. And similarly here also omega 0 prime. Here also omega 4 prime. These are all 0. So in this way it is set up. Okay. So ultimately the equations are governing equations are linearized using the perturbation technique. After linearizing, we get two equations. One equation we get one equation we get for this quantity. You will ask me, I will tell you what is this quantity. One equation we get for this quantity. This we generally call it psi m prime. And another one equation we do like this, that is psi 1 prime minus psi 3 prime by 2. That is your psi t prime. These two equations we get. These two equations are not at all simple equation, quite complicated equation, but ultimately we get two perturbation equation, one for this one for this one. Okay, acha, we get this one, and this psi 1 prime, psi 3 prime, these are nothing but perturbation stream function, this one. Okay, acha, fine. And another one thing also, that is we got two equations, and in these two now, and since we are analyzing the Baroclinic instability, so ultimately, as I told you, this is also an wave instability. Therefore, instability perturbation is thought to be in the form of a wave. So accordingly, actually, we take this thing, that is one is just, let psi m prime is equal to a into e to the power I k x minus ct and psi t. It is a very simplified treatment. Actually, both the thermal, we call it, this is a thermal perturbation, and this is the mean perturbation. This is the mean perturbation. This is the thermal perturbation. This is wind perturbation, you can say. And this is your b e to the power I k x minus ct. So as I told you, that ultimately we got two equations in psi m prime and psi t prime, and in these two equations, these two are substituted, and after you substitute these two, ultimately you get linear equation like this. Just this type of linear equation you get, that is, say, LA plus MB is equal to 0, and another one, say, alpha A plus beta B, this is equal to 0. This type of two linear equation you will get in terms of AB. AB are nothing but amplitude of these two perturbation. So now one solution immediately we all can see, that is A is equal to 0, B is equal to 0. That is your trivial solution, which we are not at all interested. We are mainly interested under what condition these two equation gives non-trivial solution, that may, and for which actually this quantity should be 0. This quantity should be 0. Now, when this is expanded, then actually, we get a quadratic equation in C minus UM bar. You get a quadratic equation in C minus UM bar. UM bar is nothing but this is nothing but, this is your U1 bar plus U3 bar divided by 2. Similarly, UT is also there, that is your UT bar. This is also U1 bar minus U3 bar by 2. This is your mean thermal wind, and this is your mean zonal wind. So you get an quadratic equation in C minus UM. And you remember that I already told that for instability, we need a very specific condition, specific thing, that under what condition Ci, that is the imaginary part of C, should not be equal to 0. What does it mean? It means this quadratic equation should have imaginary root, and that also we know the condition, that is b square minus 4ac should be b square minus 4ac should not be equal to 0. So now question is, so when we are analyzing this thing, that is b square minus 4ac, then it is a very complicated equation. Actually. So now from that complicated equation, actually one condition, one situation is analyzed, that under what condition this discriminant is equal to 0, that is a neutral. Where under what condition this discriminant b square minus 4ac will be equal to 0. As I told you that ultimately you will get one quadratic equation. So let me write this quadratic equation. Let us say this quadratic look like that: p into this is equal to 0 plus q into c minus um, this type of um plus r. This is equal to, this is the quadratic equation. And question is, we know very well that is, for imaginary root b square minus 4c, that is q square minus 4p into r. 4pr should not be is equal to 0, and it should be less than 0. It should be less than 0. Okay, so now this is the equation. So first, what is this? Try that. Let us make q square minus 4pr is equal to 0. So let us analyze the neutral condition, and from there actually one graphical relation was obtained. Graphical relation between two quantity. One is your say, let us write y, which is proportional to ut bar, and another one is your say x, which is proportional to k square. K square is nothing but k is nothing but the wave number of the perturbing wave. And then if I plot, then you will get one curve like this. Every point, and this is your x, as I told you, this is proportional to k square, and this is your y, which is proportional to ut bar. This purpose, and every point on this equation, these are, it is a neutral. Neutral means this one, that is what I was telling you, that q square minus 4pr is equal to 0. That is, this is your q square minus 4pr is equal to 0. And every point outside, this is greater than 0, and every point inside, that is your q square minus 4pr less than 0. Okay, and this curve is known as neutral curve. Now let us analyze this curve. Now suppose I am having a certain amount of baroclinicity, which is given by this point, this line. So now let me draw one line like this. So now look at here, every point on this line is outside this curve. So therefore, every point on this line will correspond to baroclinically stable. That means if any perturbation is inserted, that perturbation will be just killed. Okay. So now let me increase the baroclinicity. I am increasing here just at this much. Even here also, I am getting a point just touching the neutral curve. So that is also not that for that also it is green, that means it is neutral. So now suppose this much baroclinicity, let me say this is this much baroclinicity, let me call UTC. It is a critical value of the your thermal wind, okay, which is a measure of the baroclinicity of the mean flow. Now if the mean flow is more than that, then what you are getting, you are getting all these points which are inside inside this neutral curve, and all these points corresponds to this condition, that is baroclinically unstable. So therefore from here one point is very, very clear, that mere our mean atmosphere is baroclinic, it does not mean it will give rise to baroclinic instability. Due to that, during monsoon season, even though we know our monsoon mean flow is baroclinic in nature, but still throughout the monsoon season, every day, every time, we don't get an instability. We don't get an instability. We don't get a baroclinic instability. For the baroclinic instability, this condition needs to be satisfied. This is number one. Second thing is that for any thermal wind, for any baroclinicity, which is greater than this critical value of the thermal wind, we get 2 points. Look at here, this point and this point. Any point for which k square is lesser than this, k square is lesser than this value, they belongs to outside, that means they are stable. And any point for which k square is more than this value, more than this value, they will be also baroclinically stable. Now one thing is very clear, that any point whose k square value is very lesser than this one, that means they are relatively shorter wave. And any point whose k square value is more than some value, more than some this one, that means they are relatively longer wave. So therefore what we can see, that there is some shorter wave stabilization is taking place, there is some longer wave stabilization is taking place. Shorter wave stabilization is taking place by the atmospheric static stability effect, and the longer wave stabilization is taking place by the beta effect. Not only that, this another one is also very, very clear, that if this is an asymptote, if I take an asymptote here, actually, suppose this value, let us say this is your some kc square. So therefore one thing you can see, that even if your baroclinicity is very, very large, very, very large, but for any wave whose wave number k satisfies this one, that is k square is greater than kc square, they are stable, for any ut, they are stable. So therefore you can see k square greater than kc square, but that means very soft waves. And but this kc, whatever ut, whatever utc, all those things, that depends on the mean wind, as well as your this thing, what is called that is your latitude, actually latitude. Both the things it is required. And now not only that, actually what happened, some special case can also be discussed from here. So one special case is that if ut is not equal to 0, that is if there is no baroclinicity in the atmosphere, what you will get, you will get this one. I am telling you. You will get this, both this A and B is equal to 0. Both will be equal to 0. This is number one. Similarly, if you don't take the rotation, then also some effect is there. So therefore, this is about your baroclinic instability. Now, along with that, another one small topic actually I just want to discuss with you, which is related to this one. So that is called actually, that is called zonal index. Zonal index. Zonal index. Zonal index actually how it is defined, zonal index is defined as that your mean sea level at your 35° north, and another one is your mean sea level at 55° north. Their difference. Also, it can be defined like this, that is Z 300 35° north, their average, and Z 300 55° north. Okay, their difference is called zonal index. So now that is, if the zonal index is more, then it implies strong westerly. Then your jet core to the north of its normal latitude is to the north of the normal latitude, to the north. And not only that, your isobaric pattern, pressure patterns are east-west oriented. Pressure patterns are east-west oriented. And very less meridional transport. Okay, so this is the characteristics of high zonal index. And that low zonal index, we all can understand. It will be just opposite. Westerly will be weaker. Jet core will be south of its normal latitude. Pressure patterns will be mostly north-south oriented, and significant meridional transport will be there. So from these two, one thing is very, very clear. Under what situation we can get a deep penetrating westerly wave? Quite natural. We can see that is your under what condition? That is our low zonal index condition. We will get that. Now question is, this low zonal index condition arises due to this baroclinic instability only. That means when the mid latitude, this is mid latitude, sir, 35 to 55, this belt, when this belt becomes baroclinically unstable due to increasing the baroclinicity, that is north-south temperature gradient, then this mid latitude this become baroclinic unstable, and then only this your what is called deep that is zonal index becomes low, and then we are getting all this type of thing. That is our jet core. Jet core means, I mean to say, westerly jet core to the south of its normal position, and your pressure fields mostly north-south oriented. Even you must have seen, sir, that whatever recent depression has gone, actually I don't remember that isobaric pattern. It was not perfectly, actually it is mostly, it was north south oriented, if I correctly remember. So I also analyzed 1-2 days on a field, pressure field. So yeah, even that even the streamline pattern, circular this is also to some extent north south oriented. North south oriented was there. Exactly not north south oriented, maybe northeast southwest oriented like this actually. So actually these are all indication of your what is called baroclinic instability. So and another one thing, that is very good research paper is there by your in the Journal of Atmospheric Science. That is your our Misra ji, SK Misra, and our madam who was IITM director actually, madam name I am forgetting. So in that paper they have computed, they have investigated the baroclinic instability in a mean monsoon flow. It is a very old paper but very useful paper. They have found, as you have seen na, in a baroclinic instability you are having two end. One is your shorter wave side, another one is a longer wave side. They have also found in the shorter wave side they found it is monsoon depression, and in the longer wave side they found tropical instability. And hence we stop today. Thank you very much.
Thank you so much, sir, for the wonderful lecture. Before moving to the question answer section, I will request everyone present here to please switch on their cameras for a quick photo session. And I also request all participants present to please write their questions in the Q&A box. Thank you, everyone. Now I request Dr. Millie Ghosh ma'am to please conduct the Q&A session.
Thank you, Mrinal. There are two questions by Joshan. The first is, sir, can you explain this in connection with monsoon onset? I think it is context with zonal index, I think. Trough formation, active and break and withdrawal of southwest monsoon.
So first of all, let me answer first question. That is that is onset. You are telling the onset, monsoon onset. As I am telling you, that is during summer season over the northern hemisphere, summer, and that time actually eventually there is cold season in the southern hemisphere. Strong north-south temperature gradient starts developing, and due to this north-south temperature gradient, this belt becomes a reservoir of zonal available potential energy. And as I told you that when this temperature gradient, this baroclinicity exceeds a limit threshold, then these bursts take place actually. This monsoon flow comes actually. This is the onset actually. This is the onset. And an active break, not only that, sometimes actually onset also gets affected due to the passage of mid-latitude deep penetrating westerly waves. Because if the passages of these waves continues in our monsoon season itself, that time what will happen? We have seen in the mid-latitude westerly, there is one part is that is northwesterly. This northwesterly wind, when it brings the colder air over our northern latitude, that is our Rajasthan, that Jacob over that area. So as a result of which, whatever heated they should be, they can't get heated that much in time. As a result of which, the required horizontal temperature gradient resulting into required pressure gradient doesn't develop. As a result of which, monsoon current becomes weaker. Because you see, ma'am, that the monsoon current requires energy. It is a run is there, na? So much run is there. When I am running, taking part in a running, I must ensure that I am having energy. If I don't have energy, I cannot run. It is also running. Air is running. Air is running. For that, it requires huge amount of energy. And this huge amount of energy is provided by this north-south temperature gradient, zonal available potential energy. And in any case, it should not be interrupted. If it is interrupted by continuous passage of our mid-latitude deep penetrating westerly waves across our longitude, means our country's longitude, then in that case definitely. And another one thing, suppose monsoon onset is over, monsoon has taken place also, monsoon is going on. That time also sometimes what happened, due to the passage of this mid-latitude westerly wave, again this north-south temperature gradient becomes reduced. So as a result of which monsoon currents sometimes become weaker. That time also we are getting less monsoon as such.
Thank you, sir. The second question is, secondly, how we can include clouds, precipitation, and latent heat release during monsoon other than eddy potential energy and eddy kinetic energy?
It is a very good question. Actually, I will congratulate that person who has now.
Joshan, the question.
So first of all, zonal available for the development of the zonal available potential energy, as I told, that warmer region should be more warm. Now, warmer region will be more warm due to heating only. Otherwise, there is no other things are there. So now, for heating, we have two mechanisms. One mechanism is latent heat, another one is your sensible heat. Sensible heat is our sun, and latent heat is that is cloud. Now question is, in the cloud it has two roles actually. Cloud may intercept some solar insolation also, and cloud intercept some outgoing long wave radiation also, and rain, definitely due to rain, this latent heat also contributes very significant role in the heating, actually.
Thank you, sir. The other question is by Dr. Ira Upadhyay.
Hmm.
She has thanked for a very excellent lecture. And her question is, do noticeable correlations exist between the phases of baroclinic waves and the anomalies in the air quality index recorded of surface stations?
Pardon, sir, I will not getting your question.
Do noticeable correlations exist between the phases of baroclinic waves and the anomalies in the air quality index AQI recorded at surface stations?
Actually, I have not started. Actually, I don't have a knowledge. But one thing I am telling you, what happened, Professor Krishnamurthy's one lecture I have heard actually. He had a paper also. So what happened, what he has shown, that due to your pollution actually, that is your, he measured it in terms of what is called optical depth. Aerosol optical depth. So what happened? So aerosol optical depth also, it is a measure of pollution, I can say.
Yeah.
That if the aerosol optical depth is more, if the aerosol optical depth is more, then definitely we can understand the solar insolation received, it must be also less. That means sensible heating will be less. And if the sensible heating is less, then definitely it has something to do with the baroclinic instability, because as I told you that baroclinic instability occurs when there is heating over the relatively warmer region. So now if this heating is affected due to some significantly more optical depth, leading to significantly reduction in the solar insolation, then naturally heating will be less. So definitely in that case there will be effect on the baroclinic instability.
Thank you, sir. There is no more question, and thanks for a wonderful lecture and very detailed explanation, sir.
Thank you.
Over to Minal.
Thank you, ma'am. Thank you, sir. Before moving to vote of thanks, I would like to tell a quick feedback of today's lecture. Total 57 participants were present today throughout the lecture, and over 90% of participants have rated today's lecture as excellent and very good. So this is today's stats. Now I request Mr. Dr. Ashwin Zadhav from SPPU to please give vote of thanks and conclude the session.
Thank you. Mehul. Thank you. I'll share my slide. So on behalf of the organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 19th lecture in our weekly online lecture series on atmospheric dynamics and its application to climate sciences. We are especially grateful to Professor Ajit Tagi, President of SAMA, for his welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Dr. Somenath Dutta, for delivering an enlightening lecture on Baroclinic instability. I would like to acknowledge Ms. Mrunal Naik for moderating the session and Dr. Mili Ghoshni Lala for efficiently managing the question answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members. A special thanks to the participants and attendees who joined us from across the globe and to the dedicated team members at Savitribai Phule Pune University for their invaluable role in organizing this lecture. Thank you all. Thank you so much.
Just a minute. Actually, I saw during the talk that there was 2 hand raised. So if they have any question, I will be happy to reply. I saw there was 2 hand raised.
Actually, sir, they can raise hands, but they have to type the question. They can't talk or join this conversation.
Oh,
But so they, unfortunately, they have not typed their questions here.
so
We will encourage them to type their question or mail their questions to Dr. Somenath Dutta.
okay, sir. So should we?
Yeah, so then we'll
Yeah.
conclude this exercise. Yeah. Thank you, sir. Thank you so
Yes.
much.